Okay, guys, first, just to revise, we were discussing about bimolecular collisions last time, and today we'll focus on real gases. And also we'll solve few problems, some good questions which I have kept it in here, so we'll discuss them. Right. One second. Okay, guys, let us start now. See, when it comes to van der Waal real gas, there are two important assumptions which we take. One is we do not ignore, okay, we do not ignore volume of particles or whatever be the size of particles in comparison with the volume of container. So this is one part we do not ignore usually. Second thing is the intermolecular forces. So intermolecular forces are not ignored here. So we do not ignore intermolecular forces, which was what we used to do it in ideal gases. But when it comes to real gases, these are the two factors on which we will base the real gases. Now, one of the kind of real gases which we have to study is van der Waals real gas equation. Like that, there are many other equations, Berthelot's, Dietrich. So here in our syllabus, we only have van der Waal reaction, van der Waal real gas equation. So we'll focus on that. Now you can see these terms: pressure, volume, number of moles, temperature. So based on all of these terms, one thing we can say is that when it comes to ideal gases, we know we used to write PV is equal to nRT, and here this volume, this pressure, if at all I write it as ideal pressure into volume as the volume of the container, that used to give it as the ideal gas equation. Now what is the issue with the real gases is that if we consider the intermolecular forces, in case if at all I consider intermolecular forces, then ideal gas and real gas might have certain difference. Now what is the difference that you will experience? Let me show you. Suppose if you have a lot of gas particles here, and I take this as the reference gas particle which is moving towards the walls of the container. If other particles are not attracting towards it, it would have certain speed u average. Now, if other particles are attracting this particle, this will reduce the speed, so u average will get reduced. If the average speed reduces, the momentum transferred on the walls of the container will reduce, which in turn will change the force. Correct? Yeah, good evening, Ranveer. Right. So thereby we can say that the force applied would be less on the walls of the container, hence the pressure decreases. So this is one direct point I want you to remember, that while considering van der Waal real gas equation, we assume that the real pressure exerted by the gas is always less than the ideal pressure, ideal gas pressure. So the difference between them is what I'll call it as the correction factor. Right? So this is the correction factor. So how much is this correction factor and how this correction factor depends on, that is something we need to check. Okay. Now, if you observe, when it comes to this correction factor, it depends mainly on the molar density, because it is like a particle from here is moving towards the walls of the container, but there are certain number of molecules per unit volume which are attracting it, because of which its speed has decreased. So number of moles per unit volume, if they are more will be the attraction, and less will be the speed, and less will be the pressure applied on the walls of the container. This is one factor. The other factor is that when this particle is moving, we can see that the same number of particles, each and every particle, right, because of their force of attraction, as well as they are coming in between the path of this particle. Earlier that used to come, but we used to ignore the fact that the particle size is negligible. Now here, when it comes to real gases, even that part will also counter that, which means another factor n by v will come into account. So we can say that the correction factor or the pressure correction will always depend upon n square by v square. So one factor is coming from the molar density because of attraction. The other part is also an attraction part, but you can take it as what do you say, crowding. N by V is more number of crowding. More the crowding, more is the amount of correction factor which you will see. So making this into an equation, so we can say a constant will come, and this constant is what we call it as the van der Waals real gas constant. Now this constant A will always be dependent on intermolecular forces. More the intermolecular forces, more will be the value of A. So this is one correction which you will observe. So therefore, if you write the ideal pressure, it must be the real pressure of the gas plus A n square by V square. So this is the factor which you will come across. Similarly, when it comes to volume, right, there are two things you must observe here. When it comes to volume, imagine if the particle size is negligible, then this volume of the container will be same as the volume of this ideal gas. Okay, but in case of particles having certain volume, then at a time this particle will not be able to cover the entire volume. It will only cover that particular volume where this particle's volume is excluding this particle's volume, it will cover rest of the volume. So in fact, when you write PV is equal to nRT, PV is equal to nRT, this volume is exactly not the volume of the container. This volume is called free volume. And that free volume, because free volume is nothing but available volume. How much is the volume which is available for particle to move? In case of ideal gas, because the free volume or the available volume is same as the volume of the container, we take in PV is equal to nRT, we take this volume as volume of the container. But since here the volume of the container is not the complete free volume, only this much is the free volume. You can see the highlighted part, this much is the free volume. So hence, now if you check out volume of the container, that would be equal to, right, this entire volume, which is this volume of gas which is covering, right, and plus this extra volume which is called it as correction. So hence, now if you check out the free volume, that would be container volume minus the correction factor. Now this correction factor or the volume correction depends upon what factors you can see. It simply depends upon how many number of moles do we have. More the moles of the gases, more would be the volume. So I can clearly say that the correction factor is directly proportional to number of moles, or I can say the correction factor will be equal to number of moles into some constant B. Now this B is another van der Waals constant. This B is another van der Waals constant, and B directly depends upon the size of the particle. It has nothing to do with attraction or repulsion. It is mainly to do with the size of the particle. Okay. So this is the other correction factor. So combining both these correction factors, we will get the real gas equation. But let us understand what is this B exactly and how it depends on. B is also called as excluded volume, excluded, excluded volume or co-volume. What is this co-volume or excluded volume means? In here, in van der Waals real gas equation, we always consider collisions are bimolecular. So when two particles collide with each other, now how much amount of volume would be unavailable for the third particle? Suppose if this is a third particle which is approaching. For this third particle as it approaches, this entire volume is unavailable because at the time of collision, you can see it cannot come here, 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 here like this. The reason for it because we are assuming it is a bimolecular collision. We do not expect the other molecule to come and collide with the particle. So when the bimolecular collision happens, on an average, you can see how much amount of volume is not available. So you can see that, suppose if at all I write this one, yeah, here you can see like this. So these two paths, if you check out, this entire part of this, you know what I'm highlighting here. So this entire part of this would be unavailable for other particle to come and collide. Got it? Now, if you take this entire volume on an average, how much that would be? It would be equivalent. If you check out the average volume of two particles occupied, it would be equivalent to the volume of this sphere. So this sphere is how much? 2 times of radius. So which is, I can write volume of two molecules would be equal to 4 by 3 into pi. R is 2r cube. So which is 8 times the volume of one molecule. Volume of one molecule. So for two particles, the volume occupied by uh, them during the collision would be 8 times of the volume of molecule on an average. So this B factor represents how much volume is occupied per one particle per in one for 1 mole of a real gas. So which means if at all I take that B, that would be 4 times, because this is for two particles. If at all I take it for one particle, it will be 4 times of 4 by 3 pi r cube multiplied by Na, because it is for 1 mole of a molecules. So you better remember this as a formula, that B factor will be 4 times 4 by 3 or volume of the particle into Na. Combining both of them, we will get the van der Waals equation as this. So I want all of you to just make a note of this one. What is van der Waals real gas equation? So it is P plus A n square by V square into V minus NB is equal to nRT. Here the assumptions are A and B are independent of temperature. There is one more equation called Berthelot's equation, where he assumes A is proportional to temperature. Got it? So temperature factor will also come into that. But as much as van der Waals equation is concerned, A and B are assumed to be independent of temperature. So A value, another important fact is that A value of any gas will always be greater than B for any gas. So while problem solving, this becomes very important. For any gas, if you check out, its A value is always greater than B value. Okay, students?
So,
Yes, better.
can you? Okay. No, I was asking you to scroll up.
Right, check it out. This
Done,
is the
sir. I
value
copied.
of P. This is the van der Waals equation. These are two things you must take it from whatever the discussion we have done so far. Okay, and how this A and B are dependent on temperature and independent of temperature. And very important point is that A value is always greater than B. Okay. Right. Now, so therefore we can write this as, you know, A plus A n square by V square into V minus NB is equal to nRT as the equation. And here A always depends upon intermolecular forces. Anything, if you have to compare any two examples, I have not kept it here. Yeah, I'll just write the examples here only. Suppose if at all I take, H2 and Cl2. If I consider the A value of H2 and Cl2, this van der Waal attractive forces for chlorine is more because of its size. So A value would be more. At the same time, when you compare the B value of H2 and B value of Cl2, it only depends upon the size. So here also B value is more. Okay. B value remotely relates to the repulsive forces, but its major contribution is always about the size. So you should always remember that while comparing B value, you should first see the size. Okay. Similarly, if you check out H2 and helium also, A value of H2, is slightly more than that of helium, and B value of H2 will be definitely more than that of helium because this is in an atomic form, this is in a molecule form. So its size would be bigger than helium. Okay. So A value and B value of hydrogen would be more here. Got it. Similarly, if you consider any complex molecule like NH3 and CH4, now this time we can compare A value of NH3 definitely is more than that of A value of CH4. For comparison of B value, we need some more data like how is the structure, correct? But A values we can always compare because we know that ammonia will have strong intermolecular forces as compared to that of CH4 because this will have this will have dipole-dipole interactions, this will have only van der Waal interactions, dispersion forces. Okay. That way you have to figure out how A and B are related with each other. Okay. If you check out the units of A and B, A would have the units because it is A n square by V square and the unit of ATM. So if I take this A n square, I'll get ATM liter square by mole square. So that will be the units of A. While B, it is NB giving a liter 1. So N will be equal to, B will be equal to, okay, liter per mole. So this will be the units of A and B. Okay. So mostly I want you to just remember these two parts. That would be useful for problem solving as of now. Next, coming to the next important factor, that is compressibility factor. This can also be defined in many different ways. I'll write it down. Z is defined as V real by V ideal. This is one way of defining, or T real by T ideal, for it, or P real by P ideal. These are different ways of defining compressibility. In our syllabus, we are more concerned with this. What is V real by V ideal? Okay. Now, by definition, when we check compressibility factor Z as V real by V ideal, this is only valid when you have a same number of moles, same pressure and same temperature. So this can be only compared when you have same number of moles, same pressure and same temperature. Imagine this situation. Okay. Suppose if I keep one side, I keep ideal gas, one side I'll keep real gas, and try to maintain both of them at same temperature, pressure, and for the same number of moles. And here, if you can see, the volume of real gas is more. So we say that real gas volume is more than that of ideal gas volume here, which means Z value will be greater than 1. This is only possible when particles will have more repulsions than expected. Here, the repulsive forces are dominant in real gas. So wherever you see Z is greater than 1, you got to assume that there are repulsive forces dominant. Now in the second case, you can see that real gas volume is being less than the ideal gas volume for the same number of moles, pressure and temperature, and Z value is less than 1, which means attractive forces are dominant here. Last case, V real is same as V ideal, which is Z is equal to 1 and real gas is behaving like an ideal gas. So this is the important relation which you will get from compressibility factor. that if Z is greater than 1, you got to understand that there are more repulsive forces dominant. If Z is less than 1, attractive forces are dominant. If Z is equal to 1, ideal gas behavior. Okay. Similarly, I can define Z in terms of T ideal by T real. Okay. Suppose in here, if you check out, this is a temperature unit, not volume unit. Please understand that. Okay. Now here, if you can see, Z is equal to, if in case here real is greater than ideal. So what does that mean here? So this value is greater than that. So Z is less than 1. So therefore attractive forces are dominant. In case if ideal is greater than that of real, then repulsive forces are more dominant here, and therefore here Z would be greater than 1, here Z would be less than 1. And if both the temperatures are same, here the pressure, volume and number of moles are constant, then T ideal is equal to T real. Then Z would be equal to 1, and that is the ideal gas behavior. Okay. This is not for your syllabus, but in case if it comes, you got to just learn that uh, Z can also be represented in terms of temperature. And therefore, now if you check out Z, we have been written it as real by ideal. We can write this ideal part as PV by nRT, correct? Sorry, so nRT by P here. So P can come up. Well, this is the real gas pressure or ideal gas pressure is same here. So in problem solvings, you will directly get it as pressure. Okay. So it does not mean it is about ideal pressure or real pressure. Both of them would be same. Okay, just a minute. Right. So therefore, you can see that Z can be written as PV by nRT. In the questions, you would be directly given as pressure value, temperature value, number of moles value. You got to calculate Z. Okay. Don't think that given is a real pressure or ideal pressure. Both will be same. While you are defining Z, we are considering that only at a same pressure, same temperature. Okay. Right. Now this is the way to define the compressibility factor. Now, we would have an application of both compressibility factor and van der Waal real gas equation. Okay. Van der Waal real gas equation used, both of them would be useful writing a general equation called as Varial's equation. Varial equation is a general representation of compressibility factor. So this type of an equation can be written for any particular formula. That could be Berthelot's equation, Dietrich equation, and any van der Waal kind, or there are many such kinds for it. We can always represent all of them in the form of Z is equal to something like this. Okay, this is called Varial's equation. For instance, if you take for n is equal to 1, we call it as a molar volume, and I've written for n is equal to 1, you'll get this equation. Now, if at all I take this entire term to the other side, so we can know that P plus A by V square is equal to RT by V minus B. And if I take this also to the other side, I'll get P is equal to uh, RT by V minus B minus A by V square. And if you multiply and divide everything by uh, PV by V by RT, so we will get this as PV by RT is equal to 1 V by V minus B minus A by V, right, into RT. This is what I'll get. So solving this, what we will get here, we know that PV by RT is Z. So that Z would be equal to, this would be something like this. It is 1 by 1 minus B by V minus A by V RT. So if I expand this, it is like an binomial expansion of 1 by 1 minus x, which will be equal to 1 plus 1 by x plus, sorry, 1 by x plus x square plus x cube and so on, where x should be less than 1. That is a condition for this binomial expansion. So if I just use this binomial expansion here, I would get z is equal to 1 plus b by v plus b by v whole square plus b by v whole cube and so on, minus a by vrt. So if I take this thing common, I'll get 1 plus, right, b minus a by rt into 1 by v plus b square by v square, and it will be a continuous equation. So this is what you can compare a variance equation with this now. So when you compare these two, this term is becoming b and this b square is becoming c and so on. So I can write this here that capital B will be equal to b minus a by rt, and capital C will be equal to b square, and capital D will be equal to b cube and so on. So in variance equation, the first coefficient, right? So this is the first coefficient, which is actually a, and the value of a is 1 here. That is called the variance first coefficient. The second coefficient is b. So usually this is the one which is more asked, like what is variance second coefficient? So variance second coefficient is b, which is equal to b minus a by rt. The third coefficient is c, which is b square, and so on. These are all the values of second. This is the third coefficient and fourth coefficient and so on. Mostly you would be focused on the first and second coefficient only. All right. So these are the terms on which you must focus. Now, what is more useful application here, right? When it comes to variance equation, let me tell you that. Right. In
So,
case of variance equation, first thing we got to check out is what if you operate at low pressure? Yes, beta.
hello, sir.
Yes, beta. Tell me.
So, how did you calculate the third coefficient?
This is a continuous equation, na beta. So this is the value of A, this is the value of B, this is the value of C. So C is B square. If you compare here,
And D will be
B cube.
okay.
Got it? So third, fourth, any coefficient it is been asked, you should be able to relate it. Okay. Is that okay, beta?
Yes, sir.
Right. Now, what is happening at low pressure here? See, I have written that here. So at low pressure, what is happening? At low pressure, if you check out this equation once again, so the equation is something like this: 1 plus b minus a by rt into 1 by v plus b square by v square and so on. Now at low pressure, the volume will be very large. So this factor would be very small contributing, or rather this is almost ignorant. So we will be ignoring all these factors, b square by v square and anything further. So if you ignore all those factors, now the equation will turn out to be z is equal to 1 plus b minus a by rt, okay, into 1 by v. This is the equation it will turn out to be. Okay. Now at low pressures, now you can see that at some point, imagine if z is equal to 1. Okay. If z is equal to 1, then this 1 minus 1 becomes 0. So if z is equal to 1, then b minus a by rt will be is equal to 0, which means I'll get a temperature called Tb, which is equal to a by rb. And this temperature is called Boyle's temperature. So which tells us that Boyle's temperature is that temperature where the real gas is behaving like an ideal gas, but it is limited to only low pressures. Okay, so at low pressures, we will see that. Now, from here, we got what is Boyle's temperature, and let us put the conditions around Boyle's temperature. What if the second virial coefficient is positive, which means Z is less than 1. So if Z is less than 1, this value b minus a by rt would be greater than 1, because if you check out this 1 to the other side, then b minus a by rt will be greater than 1. So here I will say that b minus a by rt, if z is less than 1, right, uh, then that would be, sorry, greater than, less than 1 only, because z is equal to 1 plus b minus a by rt into, so imagine if z is less than 1, correct? If this is less than 1, which means this part has to be less than 1 only, or else it will become bigger value. So b minus a by rt should be less than 1. So I can say that temperature of a gas would be less than a by rb here, a by rb. Same way here, b minus a by rt, if z is greater than 1, this will be greater than 1, and temperature of a gas would be greater than a by rb. What is this telling us? See, if this value is less than 1, temperature of a gas is less than Boyle's temperature. Got it? So z is less than 1, we know attractive forces are dominant, correct? So temperature of the gas, if it is less than Boyle's temperature, attractive forces will be dominant. While temperature of a gas, real gas, if it is greater than Boyle's temperature, repulsive forces will be dominant. This is what mathematically we can conclude. Okay, students? And how I can write that here? Check it out. Suppose if at all, I'll put a separate graph here. I've not kept that. Okay, I'll put that graph. Suppose you can see here what is exactly happening at Boyle's temperature. Boyle's temperature, if this is Z versus P, got it? If at all I draw this as Z versus P, right? Then at Boyle's temperature, what is happening? Almost Z is equal to 1 and it is moving like this. That means at low pressure range, it is behaving ideal. So this is a real gas equation which is behaving ideal. But anything more than the Boyle's temperature, if this is Boyle's temperature, and if you are operating anything more than Boyle's temperature, it will be repulsive forces, which means Z is always greater than 1. And if temperature is less than Boyle's temperature, then Z will be less than 1. And this is limited for low pressures. How it is going after that, we don't know. But up to this graph, up to this shade, up to this region, we know that this is how the behavior is. Okay. Suppose you can see the same graph here. If this is the Boyle's temperature, above it, Z is always positive. Below it, it is always negative. Okay. But this negative will again get back to positive, maybe at high pressures. But at low pressures, we know that it is always negative. Okay. So this was twice given in JEE, once 2004 and 2007, same graph like this. Got it? And he wanted us to analyze what exactly is this graph, what are the terms here. So this represents Boyle's temperature. This graph represents greater than Boyle's temperature. This graph represents less than Boyle's temperature. Okay, students. Now, when it comes to hydrogen and helium gas, right? You can see the size of hydrogen is greater than helium. So B value of hydrogen will always be greater than helium. And because of that, if you see Z is always greater than 1 because its Boyle's temperature is very less. So most of the regular temperatures or normal temperature which we take, which is room temperature, at room temperature we can see that Z value is always greater than 1 for hydrogen and helium. And hydrogen's B value is higher, so that's why that will be at a much higher value as compared to that of Z. Okay, this we will prove it down, as we see it for the applications of van der Waals equations. We'll be able to prove this, why Z H2 value will be more as compared to that of helium. Okay, but one thing is for sure, both of them will be always greater than 1 at room temperature, which means anything, in fact, greater than 0 degrees centigrade, sorry, if temperature is greater than 0 degrees centigrade, you will always see hydrogen and helium will lie in the Z is equal to greater than 1 zone. Yes, true. Now, how do we check out uh, the applications on the basis of different pressures. If you're operating at very low pressure, got it? Uh, I mean, around low pressure of 60 to 70 atm, then volume is still high. As you compare the volume, it is still high as compared to the number of particles. So this can be ignored. So if you ignore that and see the equation here, it will turn out to be P plus, A by V square, PV into A by V square, sorry, PV plus A by V is equal to RT. And if I take this to the other side, divide everything by RT, I will get Z is equal to 1 minus A by RTV. This is what I'll get. Because when you divide this entire thing by RT, you will get this as Z, and this will become 1 minus A by RTV. So here you can see these are all positive terms, so which implies Z is less than 1. So which means for most of the gases except hydrogen and helium, most of the gases at low pressures, Z value is always less than 1, which means their attractive forces are more dominant. Okay. But if you see it at high pressure, around 400 to 600 atm, now if you see, uh, although pressure is very high, but this factor as you compare to such high pressure is very ignorant, and volume is too small now because it is highly compressed due to such high pressure. Correct. Now this time volume cannot be ignored, so I'll ignore this as pressure can be ignored. I mean the pressure correction can be ignored here. So P into V minus B, taking it for 1 mole, is equal to RT. So PV minus PB is equal to RT, or if I divide everything by RT, I'll get is equal to Z plus 1 plus PB by RT. This is what we will get. And which is greater than 1 here, you can see. So which means repulsive forces are more dominant. So here repulsive forces would be more dominant. So at high pressure, always Z value will be greater than 1. Okay. So if you see how the gases behave, if you see in real gases, helium and hydrogen will always be with Z greater than 1. Got it? But rest all the gases except helium and hydrogen, they will have certain dip like this and come up. So even if you see carbon monoxide, nitrogen, oxygen, they will go down and come up. When the gases will go down and then raise up, we call this are making negative deviation here, and here they are making positive deviation. Positive deviation. Negative does not mean it is less than 0. Okay, negative means Z is less than 1. So that means it is making a negative deviation, and then again it is going towards positive deviation. Okay. Now, how to know how the values of different gases are? Mainly in JEE syllabus, these are the gases that would be mostly asked: N2O2, CO2, H2, H2O, NH3, CH4, SO2, and carbon monoxide. These values, you don't have to exactly remember the values of A, but you can see that more the value of A, here, check out the case here now, right? Here you can see more the value of A, Z is dipping more and more because it will become more and more negative. So Z value will become, quite less than 1. So higher the value of A means more interactions, more attractive forces. So if you compare all the values of A, we will get certain order here. You can see. So which has the highest value out of all of this? SO2 has the highest value. So A will be the most, I mean SO2 will be the most here as compared to that of ammonia, which is around 4.225. Got it? And sorry, then water H2O, then it is NH3, right? Then you can see carbon dioxide. Okay, then we have methane, right? So then we have oxygen. Okay, in fact we have carbon monoxide, and then oxygen, then nitrogen. Okay, this much you must better remember how it will be varying on the values of A. Okay, these are the cases you must know how the things are changing with respect to Z. Now, when it comes to how the pressure versus volume graph is, this is given in NCRT. Please try to understand what it is trying to relate with. Here you can just check out the value at high pressures. So at high pressures, the real gas volume is more, which means Z is equal to V real by V ideal. We know that uh, we have defined Z as in such a way. And if this is greater than 1, definitely repulsive forces are dominant. And that is what happens for the hydrogen gas. So this is given for H2 gas. So this was the graph given in NCRT for H2 gas, and it clearly tells us that Z value here, if you compare their volumes, we can say real volume is greater than that of ideal volume, and it is greater than 1. Okay, guys. So this is the first part of real gas, what you need to check as a synopsis. Now, the next important part is about critical parameters. Critical parameters is important about certain temperature, and this is that temperature above which gas will behave like an ideal gas, below which gas can be easily liquefied also. So that is a differentiating temperature. So all the pressures, I mean the pressure parameter, volume parameter at critical temperature is termed as critical volume and critical pressure. Okay. What are the important terms you must remember from here is this. These are the isotherm drawn for carbon dioxide. And in here you can see whatever it is on the right hand side here, for it, and the extreme right here at low pressures, this is all vapor state. And anything which is on the extreme left here at this high pressures, this entire zone, this is the liquid zone. And this side, it is all ideal gas behavior. And whatever the dome which is given, this is about liquid vapor equilibrium. So here we will have liquid vapor equilibrium. Okay, guys. And the one which is differentiating all of them is this temperature, which is what we call it as critical temperature. So we can define critical temperature in many ways. First thing, critical temperature is that temperature above which there is only ideal gas behavior, below which you will see gas can be compressed into liquid. Second definition, critical temperature is that temperature at which, liquid, gas and vapor, all of them will exist in equilibrium. Okay, sorry, vapor. All of them exist in equilibrium. This is the second definition.
Sir,
First,
isn't gas and vapor the same thing?
okay, beta. When it comes to gas and vapor, the difference is vapor can be converted into liquid only by compression, which means only by applying pressure. But when it comes to gas, no matter how much pressure you apply, it cannot be converted into liquid. That is the difference between gas and vapor. Yeah, beta.
Okay, sir. And also, why will the gas be in liquid state on the far left?
See, below this temperature, if you operate carbon dioxide at around 30.98 or below that, if you start compressing, which means you are applying pressure, right? Then here Z is always less than 1, which means attractive forces are dominant. So as they are dominant, slowly the gases will interact with each other, and now they are existing in a vapor phase, no beta. From here, suddenly, if you check out from this pressure, even if you increase a small amount of pressure, there is a sudden change in the volume, which suggests that the gas must have converted into liquid. Now, once it has converted into liquid, no matter how much amount of heat, how much amount of pressure you apply, no matter how much pressure you apply, what is happening? It is incompressible, right? So liquid is incompressible. So that's why it is not changing the state. It is being in liquid state only. Is that point
Okay,
clear,
got
Beta?
it, sir.
Yeah.
Yes, sir.
And another important area which we usually tend to forget. Well, this is given in NCRT, so I would suggest you guys better remember this shade which I'm making, right? This shade. This shade is called supercritical fluid, SCF, supercritical fluid. Here, it's very difficult to differentiate the gas and liquid. Understood? It is just above critical temperature, got it, and at a very high pressure. Now tell me about one simple thing. If you have water, you know, being heated in an open vessel and water is heated in a closed vessel, it is heated in a closed vessel. Okay. In which case do you see the boiling phenomena happening? In which of these two cases boiling will take place? First of all, you got to understand what is the difference between vaporization and boiling. Okay, vaporization, when we say, when we use the word evaporation or vaporization, it means whatever the vapors which are forming here, okay, there are some vapors which are forming above the liquid surface, liquid surface here. Now this would have certain density and this would have certain kinetic energy, while liquid will have certain density and liquid will have certain kinetic energy. Got it? Correct. Here these two will be different. So density in the vapor state will not be equal to density in the liquid state when the evaporation is happening, when simple evaporation is happening. Okay, and same thing with the kinetic energy also. Kinetic energy of these particles will not be same as kinetic energy of these particles. One second. Sorry guys. But when the boiling takes place, Nabita, boiling is that situation when the entire liquid has got sufficient energy to easily convert into vapor. So the entire bulk can easily convert into vapor. That is only possible when the density of this vapor and density of liquid is almost the same, and kinetic energy of all the particles in the liquid state is same as kinetic energy in the vapor state. Then we say the boiling is started. Correct. I hope you understood the difference. Now my question is, if I keep an open vessel and if I keep a closed vessel, where does the boiling take place? Okay, right. Open vessel will boil. Correct. The boiling will take place in open vessel, not in the closed vessel. Got it? What happens in the closed vessel? Closed vessel, slowly after some time you will see the rate of evaporation will keep increasing as you keep heating. The state will only change. It will come to a certain state, got it, here, where you cannot differentiate. एक point ऐसा आ जाएगा where you cannot differentiate whether it is a liquid or a gas, got it, or liquid or a vapor. Such type of phase is called supercritical fluid. Okay, students. So such type of a phase where you cannot have a phase boundary defined, that is called supercritical fluid, and which is what you will observe when you are operating just above critical temperature and at a very high pressure. So at very high pressure around the critical temperatures, you will see this kind of an existence will be there, where you cannot differentiate whether this is a gas or a liquid. They like examples how the gas fuses out from the deodorant bottles, because it is maintained at such a high pressure. The minute it comes out, it is coming as both liquid as well as vapor, so it would have both the feel of it, but you cannot differentiate whether it is a only liquid or a only vapor. So such type of state is called supercritical fluid. So I think you understood how the graph depicts here, what are the areas in this particular graph. Now suppose if I consider any particular temperature in JE, what type of questions I've asked, let us focus on that. Once there was a question asked like, what if I started from this point, now I want to reach to this point, this is point A and point B, what are the ways I can do it? Got it? What are the different ways by which I can do it? Sorry, point B, let me put it here, yeah, on this, yeah. What are the ways I can get it? If you are at a point A, you can directly do compression. So while you do compression, you can see first it was a vapor state, then you will have vapor liquid equilibrium, and finally you will get to the liquid state. Okay, students, so this is the way you can get it, which means was there any phase difference which you observed from A to B जाने के लिए? क्या हमने कोई phase difference check किया? Yes, there was a phase difference here because initially there was only vapors. पहले सिर्फ vapors थे. बाद में एक particular point आया जहां पे हमने थोड़ा सा liquid देखा, correct? And finally we found a situation where there was completely liquid, which means at certain phase I was able to identify the phase difference. ना liquid बन रहा है ये हमको दिख रहा है. With our naked eye we are able to see that. So from A to B, definitely there is a phase difference. But suppose instead of approaching this way, what if I go this way now? I want to straight away increase towards this volume, which means what I'm doing, I'm increasing the pressure at the same time I'm increasing temperature. And imagine if I increase the temperature and reach to this point. Now from vapor, I tend to make it as a gas and I came to point C. Imagine I came to point C. Do I find any phase difference between A to B, A to C? A to C, no phase difference because vapor और gas में कुछ difference दिखेगा ही नहीं. No phase difference. Same. Imagine I came up to almost like this and I started compressing. Got it? And I came to point D. ये तो अभी भी gas में ही है. Gas to gas, no phase difference. Got it? And from here again I started decreasing temperature and I came to this point. Till this point also there is no phase difference. But now even if I decrease the temperature or increase the pressure, I won't be able to find much difference here, right? अब पूरा liquid में convert हो जाएगा but कोई phase change दिखेगा ही नहीं. You will not see like there is a change in the phase here because you are passing through a supercritical fluid. Got it? So there won't be any distinct
Sir,
visible.
could you explain the last part again?
Beta. I'm
From
saying
D to
from
E.
okay from D to this point, is there any change in the phase beta? It is still gas, no? Gas and
Yes.
gas. But this gas is such a kind of a gas where you are able to see like sprinkles of water, isn't or not? Like a shower or like a deodorant, isn't or not? But you will feel
Yes.
just like a gas only. And just try to decrease further temperature. Okay, if you just increase the temperature further, what would happen? Everything will look like a liquid now, but there won't be distinction between a vapor and a liquid like this phase which you are getting here. Is it or not? You won't be able to see this. You will directly see that entire liquid, entire supercritical phase is converted into liquid. Got it? So there won't be
Okay,
any
got it.
distinct boundary you will find. So this was the question given in JE once, that if this was the path drawn, how many phase difference you will see? 0. If you go through this path, there is one phase difference you will see. Is the point clear? So this is the type of theoretical questions you should be able to answer. Okay. Remember what is supercritical fluid, how it exists in this area. Okay. Questions have been becoming frequent in this area. Now, mathematically, what it is useful. If you observe how the graph here is, it is coming something like this and changing, especially at critical temperature. So basically, it is changing. It's something called concavity. Right? At this point, where you have critical pressure and critical volume, we can see that for every gas at critical temperature, critical volume, and critical pressure, concavity changes in PV graph. This is a PV graph. So concavity changes. Concavity, where the concavity changes, it is called inflection point. Right? So it is called inflection point. In calculus, you may have heard of it as inflection point. At inflection point, what you'll observe, the first derivative, okay, is 0, as well as the second derivative of that function is 0. Got it? So we can use these 2 points and try to calculate exactly what is PC, TC and VC. Okay. We know that pressure, into pressure plus A by V square into V minus B is equal to RT is an equation for N is equal to 1 for real gas. So I can write pressure in terms of RT by V minus B minus A by V square. And if I differentiate this, first differentiation and second differentiation, so dP by dV एक बार करूँगा and उसको equal to 0 कर दूंगा. Got it? Here also I'll equate that to 0. D square by P and dV square equal to 0 कर दूंगा एक बार. So दो equations आएंगे. When you solve both of those equations, I will be able to get three very important points. VC will be equal to 3B, TC will be equal to 8A by 27 RB, and PC will be equal to A by 27B square. This is what you will be able to derive it. Okay, so I'm not differentiating that. You can differentiate that very easily and get it. Or you can do it in an algebraic way also. You can see here, come to this point. देखो यहाँ पर ideally behave कर रहा है अभी भी P versus V. यहाँ पर तो ideal है ही. The only area where the gas is becoming slightly different from ideal behavior is between these 2 points, where it is showing mostly real gas behavior. Right? So between these 2 points, okay, if you observe this equation, it is like a third degree polynomial only. Third degree polynomial of volume, which is P plus A by V square into V minus B is equal to RT. So you can see PV plus A by V. Let me just multiply that as PV plus A by V minus PB minus A by V square is equal to RT. Correct? So this is how it is. Sorry. Right. Now if at all I take LCM on both the sides, so what I will get PV square plus A by PV square plus AV, sorry, if I take LCM I'll get PVQ plus AV minus PBV square minus A is equal to RT. B किधर गया? Minute. I'll rewrite that. Just take this as PV square plus A into V minus B is equal to RT V square. Now it will become more easy. So PVQ plus AV minus PBV square minus AB is equal to RT V square. So if at all I bring this RT to the other side, it is like a third degree polynomial. So where you will have PV square minus PB plus RT into V square plus AV minus AB is equal to 0. So we just have to solve this third degree polynomial between these 2 points. See, these two are two distinct points ना बेटा, इसमें बहुत सारे volume terms हो सकते हैं. But imagine these 2 points as it approach to this point, what are they becoming? They are becoming equal roots. So which means this third degree polynomial has something like this: V minus VC whole cube equal to 0. ऐसा root आ रहा है यहाँ पर, because all three roots should be equal at this point. And if you expand this and compare, you will get the same ABC, this one, PC, VC, TC. So these are the two methods by which you can calculate PC, VC, TC. Now check out what it is with the Z value here. Compressibility factor at this exact critical points will be PC, VC by RTC. So if you substitute all the values here, we will get this as 3 by 8, which is less than 1. Okay. So which is less than 1 implies that there is a attractive forces dominant here. So exactly at critical temperature, you'll see attractive forces are dominant. And critical temperature will always be approximately 1.6 times of it normal boiling temperature. This is BP, boiling point. So for any gas, you can always relate. In case if you want to check out what is its critical temperature, approximately around 1.6 times of its normal boiling point will be its TC. This is empirically derived, so there is no mathematical derivation for it. You just have to remember it. Is this point clear, everybody? Right? Please remember this. Along this line ना, लिक्विड और गैस के बीच में डेंसिटी डिफरेंस कुछ भी नहीं रहेगा, काइनेटिक एनर्जी का डिफरेंस नहीं रहेगा, विस्कोसिटी का डिफरेंस नहीं रहेगा, राइट? So these two will behave exactly same along this line. Okay. Last thing what you know need to know from this chapter is, another, just like we came across two important temperatures earlier, critical Boyle's temperature, and we learned about critical temperature, and last thing we'll see about is inversion temperature. Okay. For inversion temperature, we need to understand one experiment called Joule-Thomson experiment. What does this tells us? That, if I take this coefficient mu, which is change in temperature by change in pressure, got it, at a constant enthalpy, means constant overall heat. Okay, heat of the system change nahi ho raha hai. So overall heat at constant enthalpy, if you check out this mu, that is change in temperature by change in pressure, at a particular temperature, there will always be some difference here. What you will find, if mu is coming to be is greater than 0, if mu is coming to be greater than 0, which means dt, if dt decreases, dp decreases, if dt increases, dp increases, and vice versa, right? If mu is greater than 0, less than 0, which means if dp if dp decreases, dt is increasing, or if dp increases, dt is decreasing. This is what happens, right? Because if this mu has to be positive, दोनों या तो positively increase होने चाहिए या तो negatively decrease होने चाहिए. Now what exactly we are doing is expansion. Expansion means decreasing pressure. These are the two operations we are doing. Okay. So if on expansion temperature is decreasing, then mu is greater than 0, we will get a cooling effect, right? On expansion will give you cooling effect. While above, if you check out, on expansion, if temperature is increasing, which means we are getting heating effect. We will get this as an heating effect. Okay. So that is what Joule-Thomson tells us. There is a certain temperature for every gas defined, known as inversion temperature, below which attractive forces are dominant here. Attractive forces are dominant, and which will give a cooling effect on expansion. Above which repulsive forces are dominant here, and as you decrease or if you start trying to expand the gas, in fact repulsive forces बढ़ जाएगा, उसका speed बढ़ जाएगा, kinetic energy बढ़ जाएगा, therefore the temperature will increase. So mu would be less than 0, heating effect would take place. So this type of a temperature is called inversion temperature. And for real gases, inversion temperature Ti was found to be 2 times of that of Boyle's temperature. So it is 2A by RB. बस ये वैल्यू आपको अच्छे से याद करना है, and what exactly the function is ये समझना है. Is this point clear, guys? Any doubt in here? Okay. So these are the points you need to just revise once again. If you haven't understood any of this case, please go through that once again. Right? This is how much you have it per syllabus.
Last page.
Yes, beta. Yes, I'm coming. Yeah, check out.
Sir, what is TB?
T.
B. B for ball.
Boyle's temperature.
TB is Boyle's
Okay.
temperature, beta.
Okay.
Boyle's temperature is the temperature where real gas behaves like an ideal gas. Okay.
Yes.
So I suggest all of you to just go through the notes once. Now, let me take you through some good questions and we'll solve some of them here. First, we'll see ideal gas questions and then we'll go towards real gas. Let us start from here. These sheets I will send you. These are the sheets of around 50 questions totally, out of which I've selected few good ones. So for these kinds, in case of exam, if you come across this, just check out how to do this. Okay. So let us try this question now. First, a gas dissociates into closed rigid container of volume 0.16 liters as per the reaction. If degree of dissociation of A is 0.4 and remains constant in the entire range of temperature, then correct P versus T graph is how much? See, basically what he's saying, 2A is giving 3B plus 2C. So for these type of questions, either the number of moles would be given. If it is not given also, you can just take it as some A moles or B moles like that. Here it is given 1 mole. So I'll start with 1 mole. Initially this B and C are not there. Then after some time, it would start dissociating. Some X moles have lost, let's say. Then how many moles of B and C will be formed? 3x by 2 and 2x by 2, which is X, right? So X moles of C will be formed here. Now let me tell you what is this degree of dissociation. Degree of dissociation is defined by, okay, normally call it as DOD, degree of dissociation. Degree of dissociation alpha is defined as amount lost. Always use this formula, it will be easy. Amount lost by amount initial. Okay, and this amount can be represented in many ways. उसको आप moles में लिख सकते हो, pressure में, volume में, in any case. Like for example, number of moles lost by moles initial, or pressure lost by pressure initial, volume lost by volume initial, like that. So here it is about number of moles. So you can see number of moles lost is X, by amount initial is 1. So here alpha is equal to X. So I'll write it as 1 minus alpha, 3 alpha by 2 and alpha. Now alpha value is given 0.4. Now if you see, originally when the reaction started, we had only 1 mole here. This was not there. Now we have a mixture. We have A also, B also and C also. Okay. Now he says that it is dissociating in a container of volume 0.16 rigid container. So volume is not changing. And just we have got alpha. So volume is not changing means it is at constant volume. So you can see that we can apply Gay-Lussac's law. PV is equal to nRT and this is at constant volume. So P is directly proportional to T, or P is equal to some constant into T, which will be like Y is equal to mx graph. So all of them are correct. Y is equal to mx graph I. And our objective now is to find out P is equal to nRT by V. This is what it is. So if I can just calculate nRT by V, I know what is the constant value. So what is the value of that K now? It is nR by V. Volume is given. I need to find out total number of moles of gases. Total number of moles of gases. So total number of moles of gases would be 1 minus alpha plus 3 alpha by 2. You can see सारे के सारे gases दिया हुआ है. Gas, gas and gas. So add all of them, you will get the total number of moles of gases, which will be equal to 1 plus 3 alpha by 2. So 1 plus 3 into alpha value. Alpha value कितना है? 0.4 divided by 2. So which is going to come as 1.6. So we got the number of moles. So K is equal to 1.6 into 0.08 divided by volume is also given as 0.16. 0.16. So this will go 2 times here, and which makes it as 0.8. Okay. So slope of this equation is 0.8. So which means tan theta should be equal to 0.8. So implies theta will be equal to tan inverse of 0.8. सो ऐसा आपको स्लोप ढूंढना है इसमें. सो आई होप ऐसे क्वेश्चंस आप कर सकते हो ना. एनी डाउट हियर? Okay, based on that, can you try the next one? So guys, please try the next one now, which is quite similar to that. But unlike dissociation, here it is association, but the formula lies the same. Amount lost by amount initial. Arnav, Arya, did you understand the first question better?
Yes, sir.
Okay, please try the next one. Ansh, did you learn the first one better?
Yes, sir.
Okay, do the next one.
So
Yes, beta.
then I copy the previous one. So
Yeah. Done, beta.
yes, sir.
So I'll keep writing. You are, meanwhile, you
Sir,
all
is
keep
it
walking.
0.6?
0.6, I guess so. Check. I think it should be 0.6 only. Just check the answer. This is question number 70. Yeah, 0.6. Same thing, 1 minus alpha. This will be 2 alpha by 3. So total number of moles, 1 minus alpha plus 2 alpha by 3. And tan theta is given, right? This is given as 0.8. So 0.8 would be equal to, because you know that this is 0.8, this total value is nr by v. So that 0.8 is equal to nr by v. So implies n is equal to 0.8 into v. V volume is how much? 0.0821 liter divided by R. So ये R तो वैसे ही cancel हो रहा है. So that would be equal to nR by V. So n is equal to 1 minus alpha plus 2 alpha by 3 is equal to 0.8. So implies alpha plus 2 alpha by 2. So should I take this as 3 alpha? So it will be minus alpha by 3 is equal to 0.2. Sorry, plus 0.2. So alpha is equal to 0.6. Check everyone. You must have got that. Finished? Any doubt there? Shall we go ahead, everybody? Ranveer, did you get that, beta?
Yes, sir.
Try the next one. First check what is given. Volume is given 8.21. Number of moles are given. Temperature is given. First part is to calculate the pressure, which is pretty easy. Okay. I mean, these are options, but it is based on the options. Is asked the pressure is 6 atm. Just check out whether it is 6 atm or not. Second
Sir,
question.
is it multi-correct or just single
It is
correct?
multi-correct, beta.
Okay, sir.
Sir, 6 ATM is correct.
Right. So A part is correct, right? Vedant, are you following this, beta?
Yes, sir.
Okay, keep your camera on. Vedant, Ranveer, Ishan, keep your camera on. Everyone. Yeah. Keep working. Ranveer, you got the first one? Okay. Do the second part. So if it is an open rigid container, its pressure increases to 8 atm on heating to 400 kelvins. Is this statement correct or? Please understand, when it is an open container case, okay, so if we have any gas here, sorry, if at all we have any gas here, and it is an open container case. In open container, what it is, initially before you apply any temperature, the pressure here, pressure of the gas and pressure ATM are same. Then only gas will be present here. Okay. And volume of the container is virtual volume. This is a virtual volume. And this virtual volume is constant. It is not changing. So the only thing that is changing is number of moles and temperature. Always remember, in open container cases, you will use this formula. N1T1 is equal to N2T2 at constant pressure and volume. This is open container case always. Okay. So a lot of questions have come in JEE mains which are of open container cases. You just have to apply this. Where is the volume is constant, pressure is constant. Okay. So tell me, is the second statement correct? Because if it is an open container, does the pressure change here? No, right? Pressure would remain constant. Only number of moles are changing. Understood? Tanveer, did you follow that? Yeah. See the next one. If it is a closed non-rigid container, like volume is changing now, then what is happening on heating? Now the minute it is closed, which means number of moles are constant now. Now the number of moles are constant. So if number of moles are constant, what is the formula you would apply? P1 V1 by T1 is equal to P2 V2 by T2. Now check if the option is correct. So original number of moles are constant. Okay. Tell me whether the statement C is correct. Ansh, okay. Right. Ansh, check D option beta. D option once again.
Yes, sir.
See guys. Third, it is a closed, non-rigid like skin ball. Its volume increases to 16.42. Matlab, it is sufficiently big in size so that the pressure remains constant. So the only factor that it will change is volume then, because number of moles are anyway remaining constant. So if the temperature is changing from 300 to 600, तो volume भी double हो जाना चाहिए ना? So this is a correct observation. Is the point clear? Since it is a closed container, number of moles are constant. Since it is a skin-like ball, which means the ball is sufficiently large that you are not seeing any pressure difference inside. Then temperature and volume will be the dependent factors. So V1 by T1 should be equal to V2 by T2. Last factor. When connected with another similar container, see this is an important part. When connected with another similar container, correct, which is maintained at 150 kelvins, okay, which is maintained at 150 kelvins, while original container is maintained at 300 kelvins. Now the pressure reduces to 2 by 3rd atm. Is this point clear? Okay, so originally it was closed here, and what are the conditions here now? Pressure originally was 6 atm, which you have calculated. Temperature is 300 kelvins. Volume is 8.21 liters. Number of moles are 2 moles. This was the original case. Now when you open this, gas gas will flow from this container to this container. Let me call it as container A and container B. Okay. And he said this container is similar, which means after opening it, we will get a final pressure here. I'll call it as P final. And since it is open, the pressure on both sides will be same. Temperature here will remain same. This I'll call it as TA. Volume will remain same here. Number of moles will be changed. Number of moles will be some X moles have lost. The same thing will happen on case B here. So final pressure will remain same. Temperature will remain same as TB. And volume is same as that of A. So both of the volumes are same. Number of moles here are X. So यहाँ पे hint क्या है बेटा? The pressure on both sides is same ना? Equate that always for these type of questions. So since the pressure is same, what can we say? So pressure would be NART by V is equal to NBRTB by V. TA by V and TB by V. Volume is constant, correct? So from here, can you relate that Na is 2 minus X into temperature is 300 is equal to NB, which is X into 150. For that, so this is 600 minus 300. If at all I take this to the other side, we'll get 450 X. So X is equal to 600 by 450. Okay, beta. So which is how much? I'll get this as 2 by 15, right? Sorry, that will get cancelled. 6 by 4.5. Just let me put it this way. Okay. Now these are the number of moles which are present in B, and number of moles present in A are how much? X2 minus X. Now the question is, pressure is reduced to 2 by third volume. Original pressure was how much, beta? 6 atm. Now calculate the final pressure. So final pressure would be equal to NB, number of moles of A, which is 2 minus X, right? 2 minus X. Either I can calculate here this side or this side, it doesn't matter. Let me calculate on this side. X moles are 6 by 4.5 into R. R is 0.0821 into T. T here is 150 given, divided by volume. Volume originally given as 8.21. So this goes 100 times, and here we have 6 into 15. So which means 1.5 divided by 4.5. Okay, beta. So this goes 3 times, this goes 2 times. So kitna ho raha hai final pressure? 2 atm, not 2 by 3 atm. So that option is incorrect.
Sir, instead of doing all this, why don't we just find out the number of moles in A and number of moles in B, and then equate them to 2? Usse we don't even have to get the variable X. We can directly equate it.
But both the number of moles will not be same, na beta.
Yes, sir. So we can get that. We know pressure, volume, and temperature of each container. So by PV equals to nRT, we can get N, and then you add those N, and you should get Q. And via that
Which
also
is
you
the
get the
same thing.
pressure
It's the
equals to.
same thing here, right? Which is the same thing as using the number of moles. Correct. What I did is I just equated pressure. I took the number of moles lost to this side is some X. This side we have 2 minus X present. I equated the pressure. That will also give me the same equation which you are talking. Eventually it will give me the same equation of number of moles. Okay. So
Yeah.
once I get number of moles, I'll get the pressure. Okay. So what are the correct options here? So one A was correct. The other option C was correct. Only these two are correct options. Okay. So this is a typical question. You must be able to solve this. Ranveer, any doubt here? Okay. Good. Samarth, you understood better?
Yes, sir.
Now try this one. On a similar lines. Now you should not make any mistake. Right, Ansh, that is correct. It is decreased by 2/3, not to no, not to 2 by 3. Correct. Please try this question now. This is also multiple correct, okay? I'm taking this container 1, container 2. I'll just keep working here. Just check out whether you are getting it right or not.